I started as AET's new application specialist at the beginning of September. Um, and we've been wanting to get these Tech Tuesdays going for some time now, and our goal is to do monthly meetings where somebody, myself for starters and primarily, will be giving a brief presentation followed by some topical discussion. And down the road, perhaps we'll invite some guests along. We'll be covering a lot of different topics, and of course, everything revolving around the digital fabrication workflow primarily. And today we are focusing on 3D printing mechanical assemblies. And I'm going to, this is our this is our first kind of, or my first official one. So, fingers crossed, everything goes well. I already had my camera on my laptop crap out on me, so. But I got my phone on now, and hopefully everything will be going well. So I think I'm just kind of jump in and give you just a quick presentation about using CAD assemblies in the 3D printing workflow. And I would love to have some just discussion that answers some questions you might have, hear from all of you. I do have a couple of questions I thought of myself that I would love to kind of invite you to explore, and we'll get into that after the presentation. All right, so I am not a big slideshow person. I like to keep my slides very, very, very short and do a lot of kind of hands-on demonstration. But I just wanted to open up with a few points. So first of all, I want to invite any of you to feel free to stop if you have questions. If you don't know where your the chat box is, I'm actually going to type into it right now, but you can jump into the chat and ask a question if you'd like. And if there's something that you're not clear on, this is really probably one of my something I'd love to focus on. If I cross something in this presentation where you have never heard of it before, or you really feel like it warrants like, oh, could you stop and please explain that? I would encourage you to do so. So CAD assemblies, we'll start there. Now, when I say an assembly, I'm referring to exactly what you're seeing in this slide here. And I just realized that you guys probably can't see a pointer or anything. Is that correct, Kristen?
Yeah, I can't see it. No.
Yeah, I'm not quite sure how to do it from Teams. So for the time being, I'm just gonna, I'll just kind of talk through it. But the only image that we have on this slide here is a very basic assembly that I made in Fusion 360. And of course, I'm going to be referencing Fusion 360 because that's what I primarily use, but SolidWorks, Onshape, any CAD software of your preference, all of this applies to. So what we're looking at in this assembly is 2 gears and a housing for the gears, and the housing also has axles that go vertically aligned with the gears. And my goal was just to do a very simple test and 3D print this assembly. And by assembly, we're just referring to multiple parts that are fit together. They don't necessarily have to be touching each other or connected. In this case, the assembly you're looking at on the screen, every part's separate. So no part, the housing is its own separate body, and the 2 gears are separate bodies. They're actually not touching each other. And the beauty of this with 3D printers like the Stratasys F series or the MakerBot method, or any 3D printer you might have used that uses support, dissolvable support structures, we can print these assemblies and dissolve the support structure and have like a functioning assembly. And I do have the physical one I'll show you in a little bit. So just kind of moving on here, I just wanted to talk about some fundamental basics of what we're looking at when we are exploring printing CAD assemblies. And I'm going to bypass why we would print a CAD assembly, because that's the sort of conversation I want to invite you all to discuss later. All of you are, you're probably coming from different teaching positions and different subject matter with your students. So I just want to jump in and talk about like how we kind of move through doing these assemblies. So first thing we get is accuracy of your printer and understanding the accuracy of your printer. If that's something that you aren't familiar with, you can find those specifications online. I even have a slide included in this presentation that goes to some specifications on Stratasys printers and MakerBot printers. But I will tell you that, and some of you may already know this, but that accuracy is a big variable. More often than not, what you're doing when you're working with these machine tools is you're creating a sample and you're producing your own tests, which is a very real application when it comes to manufacturing. So it's a great place to launch into with students with respect to understanding, like, what is the accuracy, what role does it play? And here I say XYZ accuracy, and I point that out because 3D printers, at least additive 3D printers, as some of you may know, are stacking layer by layer. So what's happening is our tool head is moving around on an XY axis to create one layer, and then it bumps up to the next level and does the next all on the XY axis. So really what we're looking at for accuracy, there are two elements. There's the XY and the Z. So what is the accuracy of XY? What is the accuracy of Z? They're kind of separate components in this respect, because you may find that one is a little less forgiving than the other. And that brings us to mechanical tolerance, which is the limitations of mechanical parts. So in this case, the gears that you see in the image, how close can they be together? How far apart can they be in order for them to successfully work? That's just a very baseline description of tolerance when it comes to moving parts or things that fit together. Designing test parts and assemblies themselves, of course, we're kind of just talking about that all in general right now, but this is a huge part of it. And right after I finish this slide, I'm going to show you a very simple test part I created. And the last big factor is material type. And I put that last because for those of you that have 3D printers, or even if you're thinking about getting a 3D printer and working in that environment, these printers often ship with default materials. And you're kind of like working with folks like our sales team at AET on, what avenue could you go down to get different materials? What benefits would there be? But if you're just getting into it, or you're still exploring and scratching the surface of including or incorporating 3D printing into your curricula, then working with one material is just a great control. You have just one material and you can introduce the kind of vast topic of 3D printing, like in CAD design for 3D printing using one material. But you'll find that as soon as you swap a material or change to a different type of material, then you may find your parts don't fit together properly, or the test that you did on one with one material doesn't work on the other. Okay, so what I'm going to do here, let me just open up my video on my phone. All right, Kristen, do we have this live?
Yep. Yes. Okay,
so first and foremost, I just want to, show you the this finished part here. And I made this because I really wanted to push the limits of one of our printers. In this case, this is the Stratasys F120, and that is this beautiful giant box behind me. Really love working with this printer. It's really an oven. It looks like an oven, and it's almost, you can like bake stuff in it. That's how hot it gets. But that's what this was printed in, and it was printed with a dissolvable support that, you know, when it printed from, you know, the ground up like this. And using a solution bath, we remove all that support and reveal a functioning mechanical part. Now, Dave was here when I was kind of going through just like making some tests of this. And the first model of this I did not have these cutouts in here. And I was kind of like, Dave was helping me remotely because, you know, I'm actually based in Worcester. So I was, you know, sending some files for Dave to print and asking him to put them in the solution bath. And he was like, hey, this one actually didn't work. Here's one of the older ones right here. You can see it's just flat, but I tore it open just to kind of explore why it wasn't, you know, why it wasn't working. And I think a big part that's very interesting for this design process is when you're dissolving the filament, there are very few orifices for like the dissolving liquid to move around and actually get into the crevices that have support material. So in this case, there actually was support on the outside of this cylinder here, but the only place to travel for the, you know, for the fluid is between this thin layer and the gear face. So with this design here, I created these cutouts that go all the way in, and let me see if I can get a little pointer here. Give me 1 second. So yeah, this cutout here goes all the way to the base of the cylinder, with the concept being that the liquid could come in here and actually wash into the cylinder all the way through to the other side. Same thing over here, all these little cutouts in here. And then this is, I don't know, this I just kind of did because I don't think it was 100% necessary, but I thought it would be cool to have like a little window to see what the actual, you know, tolerances, kind of highlight the tolerance of where the gears connect here. And you can see it's actually pretty spacious. It's, you know, it's not as tight fitting as I would like it to be. So that's exactly why we're kind of producing these tests here. Now I'm going to kind of put this one to shame a little bit and show you a fancier sample that a Stratasys specialist designed specifically for what we're doing today. So this is the exact same concept. He designed this in order to be printed on the F series machines. The filament gets dissolved, and it reveals this mechanical device. And this here it's still a little rocky, you know, like I'm turning it now and I'm not sure if you can hear, you probably can't hear it, but it's, you know, there's some grinding in there, and it's like, it's providing some resistance. So it wouldn't be optimal if we were looking to, like, let's say, create an actual functioning gearbox for a vehicle, you know, or perhaps a robot system, or you know, any number of applications that would use gears.
Adam, I'll let you know, because I printed so many of those things out over the years and gave them to people. I would use a little tiny squirt of WD-40. It would go so far, and also helping it with the motion. So just another little trick.
Just like regular metal mechanical parts, like on you know, any given, like a bicycle, or, yeah, that's pretty neat. What you're seeing back here, these would be like kind of preliminary tests that I would do. And before I had that on my slide, I had X, Y, and Z taking into account the kind of precision of X, Y, and Z. Actually, this one I'm gonna get rid of. And what I did here was I made these little templates that represent 0.1 millimeter or 0.2 millimeter on every side, on every face. So if I use my kind of control piece that is a set dimension, and I fit this 0.1 millimeter in, it's actually quite snug. But you can see it does actually fit. Like I can actually get this in here, but it's really pretty tense. And then the 0.2 fits in nice and smooth. And like, so bear in mind though that this is also only on the XY, the tolerance or the precision based on the XY plane. For Z, I created a little extra slot here so I can slide them in, and I also compensated for the height of the piece, so there would be 0.2 millimeters on the top and the bottom and the sides, and pretty much you get the same situation. These are all printed on the F120, so which is it's definitely a machine that I would say does a really great job of producing accurate parts. So it's a great prototyping machine, that's for sure. And I say prototyping, but there's, especially when you're working like with students, high school or university, and you're looking to produce like kind of just entry level production parts, you absolutely can do that in these printers. There's nothing wrong with that. And learn a little something about what sort of materials work best. So what I'm going to do is swap back to my screen. And at this point, I do want to invite any questions that are cropping up. What I'm jumping over to now is Fusion 360. But if anybody has any questions with what I've been talking about right now is a great time to jump in.
Yeah, I had one question about those little test prints you made. Were those 0.1 and 0.2 millimeters just based on your Fusion design dimensions?
That's right. Yep.
Okay. Thank you.
Hey, Adam, have you, so on those pieces, did you do any precision measuring at all on those to see just how well they did correspond to what you had set up for in the Fusion 360?
Yeah, I did. And I didn't document them, but they are, within probably 0.001, 0.00, between 0.00105 of the actual dimensions. So the precision is very good.
Okay, thank you.
Okay, let's see. Okay, so here we have just the two files that I've been exploring here. And for this gear set here, for those of you who are using, I would suspect this is available in any CAD, but one thing that's nice to point out is Fusion comes with a sample add-in that allows you to, let's see, where is it? That allows you to create gears. Trying to see where it is exactly. Maybe it's turned off, but it would be down here, and it's basically a really simple gear creation tool that lets you that automatically populates as a component. So let's hide the housing here and just give you a peek at what that looks like. So here's my 32 teeth gear. And when you create it, it produces the sketches that the gear is derived from. You can see here's the tooth right here. So it'll just do one tooth and then of course kind of populate that around the outer edge. It's a really neat feature. And I did this, you know, I would say I did this very quickly. If I were working with students on creating test parts like this, one thing I would focus on is the parametric aspect. So in here, you actually see I have a few values. I have tolerance offset, axle center point distance, housing width, which isn't really a big factor, but axle center point distance. Let me bring this back here. So where am I at? It's 24.6. I'll just type in 30. All right, so I would have to tie this to my housing, but you see that the axle of the housing and the gears separated. So that's one way I can control the tolerance between my gear teeth, which is a nice easy thing to do as long as you're kind of know what you're getting into there. And the other one I did was a tolerance offset. And I think I may have done that. So if we look at a side view here, this is really what I wanted. This is one of the important elements of this test here. So, and something I want to touch on as well. So if we look at our side here and do a quick measurement of this surface to this surface, we get a distance of 0.2 millimeters. Now, you can imagine if you had a 3D printer that, let's say, had a limitation of printing in 0.3 millimeters, that it wouldn't actually be able to create this gap successfully. It might try its best, the slicing software might try its best to calculate how to do it, but it probably wouldn't work out very well. So this is an interesting element when you're designing for mechanical tolerance, you're designing assemblies that have mechanical elements to them, is you know, what resolution are you printing with? And in this case, remember, I keep going back to X, Y, and Z, and separating X, Y from Z is that this would exclusively be based on your Z resolution. So if your accuracy for your layers was 0.1 millimeters, you know that you would be, you would assume you would be safe at printing a 0.2 millimeter gap between these two parts. And I should just go ahead and open up the slicing software too while I'm at it. On the other hand, for the XY tolerance, I can go into, let's see. My housing sketch here. And my diameter, these are all values that I could attribute, you know, variables to. I could say that this is just a axle diameter, and then I could say, you know, another variable would be inner gear diameter. But here I did 4.6 for my axle diameter, and the already knowing that my gear, the hole in my gear is 5 millimeters. Okay. Okay, so here I have a section analysis just to, kind of cut into the model. And this is a nice feature because we can really take a look at what our tolerances between these two parts here. And I could go in and do an, oops. I could go in and then with my analysis, you can see it actually Fusion, it populates in the browser tree over here. But now I can go and I can inspect, two faces a little bit closer, maybe that I couldn't access before. But yeah, but these this gap here is determined by the XY toolpath. Has nothing to do with Z in this case. So that's just a little bit of a a little glance into my workflow as I went through preparing this. Now, another thing I want to point out with respect to this model is this is a bad model. Like this is the type of model that I would show students, and I would say, how would you change this? Like if you were to actually use this in some sort of gear system, how could you improve it? When I looked at when I showed you the physical model like this, the body itself right here is very, very flimsy. It's you can bend it with your finger, you could break it quite easily, but these printers are capable of producing some really strong parts, especially if you're making parts that are like solid all the way through. It's pretty neat. So I think I'm going to stop here because I would love to hear from some of you. Now, I guess we can kind of go wherever we want at this point. Let me stop a share here.
Hey, Adam, question from Ted. What Z layer height was used for printing the model?
Yeah, so the, swap back over to my phone. So for this model on the F120, this was just about 0.2 millimeters, which is the lowest resolution. It's like 0.19, something to that effect, which is, I'm sorry, the highest resolution that the F120 can do. But I also did some, I don't think this one is it, but on our MakerBot method, which you can see over in the corner over here, the method, while it may not be as high quality of a part, or it may not print as fast as the F120, it can print a little bit higher resolution on the Z axis. So I went for 0.1 with that. I don't think this is. It's really hard to see, but I don't think this is 0.1. I think this was also 0.2. Yeah, but I did 0.2.
Thank you.
So Adam, we're seeing, oh, okay, now we could see. I was gonna say we're seeing your screen. Now we see the desk.
It's a nice desk.
Oh, yeah. Dave will be pleased to hear that. All right, let me pop back over to the slides here. Any other questions immediately? Because I can jump on to a couple of topics. Okay.
Adam.
Yes.
I do get questions from time to time about when you have like the hole in the bearing for your assembly there. When you're looking at the X and Y, people will ask about what the limitations of your 3D printer are the resolution it prints at in that X and Y. So I know that one of the rules of thumbs with Stratasys is that the road width is always 2 times the layer resolution. And that was a rule of thumb that I've always kept in mind. Did you apply any of that thinking to this project?
So short answer, Dave, is I did not, but you actually I like that you brought that up because I did want to open up GrabCAD here.
That would be a great place to show it, probably, yeah, GrabCAD.
Yeah. So we have our F120 here. Yeah, so what Dave is referencing, let's just slice this model, is the thickness of like a bead of plastic in this case, right, Dave, on the XY plane?
Yes, yeah, and I think you can really see it like in that. Yeah, exactly. You can see the two layers in the XY direction.
All right.
Even
Yeah,
better.
so that's a good thing to take into account. Yeah, when if you're doing like thin walls on the XY plane. So in this case, you know, I don't know if you remember when you saw my physical model, these little holes here were not, they were not high resolution. They were a little muddy, and they could have been a little bit bigger in order to maximize. We're really kind of like cutting it close with our beads of plastic here that are getting laid down. But yeah, let's see here. Yep, so another place to think about it is when you're doing something like this. Typically, by default, a wall will consist of 2 beads of plastic, which you see here on the inner wall of the gear. This is actually the gear body here, but then here is the cylinder. In the cylinder wall, probably because of the diameter of it, it did not print 2 beads, which perhaps could have improved the strength of it. So. You know, while I have GrabCAD open, one thing for those of you that use GrabCAD or other slicing software that might take advantage of this. Let's see if I think I have a file saved for this. Yeah. So sometimes I notice that when I've worked with people in you know, kind of where they're just getting started with 3D printing, a lot of folks I think are under the perception that STL is the finite file type that we use with slicing software. And some slicers may be limited to that, but GrabCAD absolutely is not. And if anything, you might benefit from importing like a native CAD file, like an a step file. Up here, you can see gear assembly sample .step. What's really neat about this in GrabCAD, and this gets really exciting when you get into printers that can do like multicolor printing and so on, or multi-material printing, but all of the components are still isolated, just like they were in Fusion. So here, if we broke them down, you see our gears, the housing, and if we pop over to GrabCAD, it is also isolated housing, spur gear. And you can even choose, let's say if you're doing some experimentation, you can choose to isolate parts of your print. And it's kind of like a hybrid of like taking your CAD file and fine tuning it in your slicing software, which is a pretty cool feature, I think. Okay, so what I'd like to do I did want to pop over to, I had a couple of topics here that I was thinking about as I spend time working with educators and hearing sort of the obstacles that are encountered in the classroom environment with digital fabrication. And I wanted to invite you to just like take a look at these and by all means, feel free to just kind of jump in if you feel like one of these is inspiring or you have something you'd like to touch on with respect to these. But I'll just read them out loud just so we can go over them. So what are the most common obstacles you encounter when incorporating 3D printing into your curriculum? This is something that I would love to hear when I'm kind of developing trainings, and oftentimes I'm kind of just, it's a short visit and I'm working with an educator on how to just do operational basics on the machine, but I always leave or try to find time to have that discussion about what is your curriculum looking like? How are you, what are your ideas? Do you need help with those ideas? Do you, you know, what sort of obstacles are you coming across after having the printer for a while? And what is the most recent innovation shared by yourself or your students? And that was kind of just one I thought about, because when I've been working with youth in the past, some of the best ideas pop up because you're just like barreling ahead as a teacher, and you all of a sudden get humbled by this one brilliant student who says, oh, well, I'm going to do it this way. And then you realize like it was a great idea. And it might even change the whole process of like a given project. And then this one kind of comes from time I've worked with schools that were specifically struggling to incorporate digital fabrication into NGSS, Next Generation Science Standards, or just like, you know, general, like standards in general. So it was a kind of general question of, are you incorporating CAD and 3D printing into those standards? If so, how are you doing it? Is it easy? Is it hard? So what do you folks think? Any thoughts on these?
I'll go first. So to answer your first question, we have the opposite problem. We have students who want to print everything and anything under the sun. So there's a little bit about, I'm from Wentworth Institute of Technology. We're in Boston. Ted Green's the professor that I work with a lot, and I run our additive facility. So we have 14 machines, I think. Yeah, 14 machines or so. A bunch of different technologies and stuff like that. But we have students that will really submit a brick, like a 4x4 chunk of material just to print down for like a weight. When you go and tell them, go to Home Depot and buy a brick for 8 cents, which is $85 in plastic. So that's our hard problem, is trying to get them to think that printing isn't the only solution to their problem. And then we also have a class here that's the Stratasys Certification 1 exam. So they go through and have to print a consolidated assembly, so what you're talking about right now, and print that out on F270, a Fortis, Formlabs, whatever we have they can use basically. And then trying to get the students to transition from machinist tolerances to printing tolerances. Also, we've had that struggle with that as well. So it's kind of a two-way street for us. I'm sure Ted could add more to that if he wants to.
Yeah, thanks for sharing that, Ryan.
You summed it up very well, Ryan. I guess the only thing I would add is that one of the things that I've tried to stress in the class is that additive, and Stratasys refers to it, and other people, of design freedom. And that's a really tough paradigm shift for students to make. And this is, you know, mechanical engineering folks of different levels, but everything, you know, they think of it in terms of traditional or manufacturing, and then they just bring that over and say, oh, how can I print it? And it's like, well, no, you don't have to print it that way. It doesn't have to be a square box. It could be, you know, just these 3 little members holding those gears together. That's all you need. And, you know, for material, to minimize the amount of material used, and it's difficult to get them to make that shift over. It just, the mind goes back to the familiar and the known. So that's an interesting one.
Can I ask you guys if, and anyone feel free to answer here, how about like maybe trimester, semester, or year-long projects that have incorporated 3D printing? Have you touched on that? Are you doing like kind of like, it sounds like you've done some short-term projects, but have you done any big, you know, almost capstone related projects? Ryan, yeah.
Ryan, go.
So through mechanical engineering, we offer we have a 2-semester capstone project. It's usually spring and summer. We're on trimesters at Wentworth, so it's spring and summer semester, so January to August or so. The first semester is the planning phase, second implementation. So we've had students that have designed a fully functioning headlight adjuster for their 1984 pickup truck. So it would move as you turn the wheel, it would turn the headlights as well. So they didn't print it all as an assembly, but they printed different parts and then adapted it to fit the old truck, and then put all the servos and wiring in there. So as you turn the wheel, the headlights turn as well. That's one of our projects. We've done other ones. I think we got canceled because of safety concerns of stuff falling from the ceiling, but we were trying, or a student was trying to make a kinetic sculpture that was printed completely. So they had this hub that they made that as weight would move up and down, it would flap wings almost like a umbrella looking thing. They were going to hang from the ceiling in the library, but then that didn't happen. But there was all one big printed part that was going to hold like feather-like wings and a weight to make it move and stuff like that. So we have done it before. We don't do a ton of it. We're getting more and more as time goes on.
Now that one, Ryan, didn't happen because the school kind of said that.
Yeah, it was the risk and compliance guy going, maybe we shouldn't hang weights from the second floor of the building and stuff like that, and have it open. Yeah.
I wonder if there are other like local organizations in the city that would bend the rules more that you could design something like that for.
It wouldn't surprise me.
Yeah. But that's cool though, yeah. Kristen, how about you?
And so in terms of capstone, so I'm at a high school, one of the vocational technical high schools, Tri-County, in the engineering technology program. And we've been printing a super lot lately. We partner with a program that NASA runs called HUNCH, High School Students United with NASA, to create hardware. And we do a lot of, we do year-long design projects with the juniors. And that most of those involve 3D printing to solve some different problems. So that's probably the best 3D printing experience for the students, because they're really working through a lot of things you're talking about, learning a lot. But then related to your first question that you had asked, what are some barriers, especially when the kids are just getting started? And I haven't done enough testing, and I haven't done really my job well enough at this point to be able to help them, but I'd sure love some help with this, is those rules of thumb. Being able to just give the kids those rules of thumb that are going to save them from a lot of headaches, especially with assemblies, with clearances and wall thicknesses and tolerances on the different machines, and all those just rules of thumb would be super helpful to just give the kids up front and say, hey, here are some rules of thumb, look out for these. And then, for our specific printers. And then related to that, what the heck was I thinking? So those rules of thumb, like the road width is, 2 times the layer resolution, that sort of thing. And then other barriers we run into is just, waiting in line on the different machines.
What do you folks have over there, Kristen?
So we've got an F370, we've got an Objet 30 Pro. We've got also have our Fortis 250 still running. So that's what we've got. But that's just the way it goes, and that's fine.
Just quickly on when I think about the rules of thumb and and creating tolerance tests, for example.
Oh, I'm sorry. I'm just going to jump right in. I remembered what I was forgetting, and it relates to what you're saying. Was some recommended test prints, to have the test, the tolerance testing, the different test prints available for the kids to use.
Yeah, so that's actually what I was going to touch on. And this is, I think one thing that I believe all of the teachers will identify with is you also have this huge obstacle of working with students that operate on a vastly different levels. So you might have a student or even a group of students who are designing way ahead of time, the ones that are sketching things out and including dimensions in their drawings and moving ahead. And you might have other students who are kind of perfectionists about testing, about creating like quality control tests, and they might kind of like get lost in that. So I wonder about assigning teams, which is ultimately reflective of like the real world career environment, where you actually have people that are technicians or technical engineers who are producing sample tests, and that the designers can then use to hone in on their final design and produce a really great functional product. Probably makes your job more challenging, honestly, and gives you more work to tackle it that way. But I can't help but think about those things, right? Because I'm sure you all know about those students, right? Where you'll try one lesson with the team, and you'll find some are just drifting off into space.
No, I actually think that would be terrific for me. That would be really a useful strategy with my kids. There are students who they struggle with that open-ended piece, and they'd much rather have a structured problem to solve. So that would be really a good thing to assign them to do.
Sure.
And by the way, Kristen's being very modest about her program. She has had some incredible students come out of that program, and the projects they've done for that Hunch program blow my mind away. I'm sure you're still doing those things. Those weren't just anomalies, Kristen.
Oh yeah, we're still doing cool things, but you know, it really is. It's kind of the exceptional student, not the typical student. And I want to be able to reach the typical student. You know, get the typical student up to that level.
She's got a gold and National Skills USA out of manufacturing, at least one, right, Kristen?
Yeah, just one.
Just one. And she's also one of 2 schools in the country, high schools in the country, that are certified for Stratus's certification program.
Cool. No kidding. That's something.
But there's so much more to do, and not nearly enough time.
So, Kristen, I just sent you an Amazon link to
I saw that. Yeah.
printing handbook. We have a bunch of them in our lab. They're very generic, as in they don't say that, you know, your F370 is this, your Fortis is that. It's more FDM is in general rule of thumb, and they're all very well written, very well pictorial laid out. There's nice pictures that show like what they should mean by road width or like aspect ratio. So we have a few copies in lab, and they're very useful for our students to look through and stuff like that. And then as far as test prints go for our students to look at, we do the simplest assemblies you think of, literally a pin and a hole. And we just have 3 or 4 pins laid out all on the same, I guess, base, and then a bunch of different rings that go over them. And they either fit, they don't fit. So they're fused, they're wicked loose, or they're nice and perfect. And we write out the ratios and all that stuff like that. We try to roll back our prints to as simple as possible. Because really everything is a pin and a hole if you think about it. So that's where we start a lot of our prints out from there.
Right. I think I make the mistake of trying to get the students to design their own tests, and that they don't have the intellectual maturity really. So that's a great idea.
Yeah, it's not
You know,
for everybody.
But I was just going to say, sometimes though, because I have thought about this, Kristen, I've just gotten involved in this fairly recently. But as far as giving the students the guidelines, I mean, we go over it, we've covered it in the slides, I talk about it, I stress it, and then they produce test prints. And half of them work, half of them don't. And it's like the info is there, but until it's almost like they have a concept that, oh, this should work. And they try it and it doesn't. And then they tend to look back and say, oh, why didn't it? And again, not all, you know, some of them will pick that up right away and go with the suggested guidelines, or maybe they'll try to tweak it a little. But others just, you know, no, this should work and I want it to go this way. And it doesn't. It's all a learning process.
Ted and Ryan, I'm sorry, you guys said are you out of high school?
No, we're actually at Wentworth Institute of Technology in Boston.
Yeah, okay, yeah. Well, I'm thinking more of high school, but quite honestly, sometimes I can see this applying to some maybe early level college students as well. But imagine that your test prints, like, can you make your test prints functional? For example, you know, just creating a very basic benchmark of something like a catapult. to launch something across a room. You know, I could see, you know, some of the starting high school students getting excited about that, with respect to just testing mechanical tolerances, and creating. And that's just, you know, a very basic idea that popped into my mind. But what other objectives could you present for the test part? Does it have to be like a boring, you know, test part like this, where it's, you know, nothing really is like, oh great, the tolerance is very, some people might get excited about that, others not so much. You need a little bit more to go on.
Yeah, I really like your idea of dividing that into functional teams and having the kids who would be excited about the test parts do the test parts. I think that would work. That would work really well.
I'd love to hear from you, if you give that a shot. Yeah, I've done that on myself, but I've also been blessed in working with youth education in very small, compartmentalized environments where I would have like 12 students. So I imagine it can be a lot more challenging when you're working with your large groups.
Right. Yeah, I'll definitely share. I'll be doing that probably on Thursday, because I think we need some of that test printing done, and I have some students to do it. So I'll let you know how it goes.